All right, welcome back. So this is an ALEKS topic that's called finding the equilibrium temperature when substances at different temperatures mix. And this is a great topic. I think it's very challenging. And I think that if you can understand this topic, then you can really get to the essence of like the whole idea of energy transfer and then the signs of that energy transfer. I think that's the hardest aspect of this type of problem. So let's go ahead and get started. The first thing I'm going to do is I'm actually just going to draw a little silly picture to illustrate what's happening in this problem. So here's my cup of water, and I've got my chunk of iron. Great art, I know. So this is my iron sample. It has a specific heat capacity that's given. It's got a mass that's given, 18 grams. And then we drop it into this container that has 200 grams of water. And they start at different temperatures. So the water actually starts at a higher temperature. Usually we do this problem where the iron is hot and we quench it in water. But this problem, it's just switching that. It doesn't change anything. So the procedure that we're going to be using is exactly the same. But the water starts out as hot and the iron starts out as cold. So there's going to be an energy transfer, right? The iron is going to be cold initially and it's going to warm up. And the water is going to cool down a little bit, so it's going to lose a little bit of energy. So just sort of identifying which is which, I think is very important. We've got an initial temperature of iron, 7.6 degrees Celsius, very cold, and my initial temperature of water, 75 degrees Celsius, quite hot. So it says, assuming no heat is absorbed, so we're just going to be transferring the energy from the hot water to the cold iron. And then our final temperature for both the iron and the water should be the same, right? Eventually, they're gonna equal out in temperature, and we should have the same final temperature. So T final for both of these should be exactly the same. So the first thing I'm gonna do is I'm gonna sort of look at this or think about it from the point of view of the iron first. And from the point of view of the iron, the energy associated with the iron, the energy transfer, is going to be Q equals Sm delta T, where S is the specific heat of iron that's given as 0.449. Then I'm going to multiply that by the mass of iron, 18 grams. And then for the change in temperature, I'm going to say T final minus T initial, and T initial is 7.6. So we don't know what T final is. So this equation here is really just sort of telling us, well, if we're looking for this energy, this would be my specific heat, this would be my mass, and then my delta T, since we don't know what T final is yet, that's what we're looking for. I'm just going to write T final minus T initial. So this is from the point of view of iron, and then I'm going to indicate that this should be a positive value, right? So if I think about, well, what's happening to the iron is absorbing energy, so I should expect that should be a positive energy gain, essentially. And my T final, that's going to be, higher of a temperature than 7.6. So this, portion here is going to be a positive number. The temperature of my iron should go up, so this should be positive, and my energy should be a positive energy. So let's think about from the point of view of the water. We're going to do this sort of same exercise. Q equals S 4.184 for water times the mass of water, 200, times T final minus 75.0 degrees Celsius. So this should be my similar expression for water. 200 is the mass of my water, 200 grams of water. Specific heat of water, 4.184. We're going to get used to using that value. And then again, T final minus T initial. Now, I should also point out in this case, this is going to be a negative value, right? This energy here, the sign for that water, from the point of view of the water, it's losing energy, right? It's going from hot water. It's going to cool down a little bit when you put that piece of iron in. And so this T final minus 75, it's always T final minus T initial. This will end up being negative value, right? T final will be less than 75. The hot water is going to cool down a little bit. So this right here will end up being a slightly negative value. If this is a negative value, then my overall calculation for Q will be negative. And what's unique or interesting or important is that the value of Q, the quantity of energy, should be the same. We're transferring energy from the hot water to the cold iron. So the value of Q is going to be the same, but the sign, the point of view, is going to be different, right? The water is going to be losing energy, while the iron is going to be gaining that energy in. So if I know that the value of these is the same, but the sign is different, then I can do a variety of tricks basically to set these equal to one another and solve for T final. Basically, I've got two equations, two unknowns, but I know there's a relationship between these different Q values from the Q of iron and the Q of water. We could actually write Q of iron equals minus Q of water, right? The value is going to be the same, but the sign is going to be different. So I think that should help us visualize the next step. So the next step, what I'm going to do is I'm going to set these more or less equal to one another with one little wrinkle. T final minus 7.6 degrees Celsius equals a negative 4.184 times 200 T final minus 75.0 degrees Celsius. So this equation here is one equation and one unknown, and these two values now should be equal to one another. So I've introduced this negative sign here, and this is just the way that I like to do it. There's lots of different ways to do this. Different instructors might be showing you different things, and that's fine. But this is the way I like to do it because I know that this quantity here should equal this quantity here, but this quantity here will be a negative value because T final minus T initial over here will be negative. Over here it's going to be positive. So if I just introduce that negative sign here, that'll just flip the sign. So that's the way that I like to do this, to show that. And now I'm just going to solve for T final. So I'm going to show my algebra here just a little bit to help you out in case you're confused on how to solve this. Basically, I'm going to multiply these through, same thing here, and then solve for T final. So if you do that, you should end up with 8.082 T final minus 61.4232 equals minus 962.8 T final plus 72210. Now I'm just going to group the terms together. So bring this minus 962.8 T final over here, bring this 61.4232 over here. So grouping terms, we should end up with 970.882 times T final equals 72271.4. And then we can just solve that for T final. So T final should equal 74.4 degrees Celsius. So that is your answer for this problem. And basically that's the procedure for any of these types of problems. Think about it from the different points of views. Think about what, type of value, what sign you should have for each of those, positive versus negative. Make one big equation and make sure that you've introduced a negative sign, if you need to, depending on, what the question's asking, in order to solve for that T final. But this is definitely one of the more challenging types of problems that you're going to run into. So 74.4 degrees Celsius, finding the equilibrium temperature when substances at different temperatures are mixed.